Hello, welcome to the class number 6. We will be continuing working with the Python script we started last class. And just to refresh what we accomplished so far, we were able to query or put together code that queries or gather the information about the object that is being currently selected. We went through the verification process of determining whether it's a valid selection made, how many objects were selected, and we proceed to calculating the velocity and the speed, storing this data into the per vertex information. And then we generated or created a dictionary variable that we will be using now to manipulate the data inside of Maya and eventually generate the image texture sequence that could be used to drive a particle simulation or fluid simulation. So I just reopened this file with the cylinder to make sure it's spinning, because during recording I created a cylinder and didn't animate it. I need to make sure that I have a movable piece of geometry on the screen so I could deal with non-zero values for the magnitude that we calculated, because if the cylinder is not moving, that on each frame the value that stored or we calculate is 0 for the magnitude of the vertex. So if I run this script that we wrote so far, then it will calculate the values for the moving object. So if I hit the highest magnitude value, if I print it out by selecting the name of the variable and hitting Control Enter, it tells me that the value that was calculated or taken from a point data dictionary is equal to 1.7. And as I just said, we would go ahead, verify that highest magnitude variable is not equal to 0 by specifying if statement. So we say if highest magnitude is equal to 0, then show confirm dialog box saying that selected mesh has no transform animation assigned. So there is no need to generate a speed map for it. So if I execute this if statement, we're not receiving confirm dialog notifying us that object is not animated because our highest magnitude variable value is not equal to 0 but equal to 1.7. Then we, as we just discussed, will go through each vertex stored in point data variable, and then we go for each frame stored within each point data vertex index, and we would divide magnitude value stored for that particular vertex by highest magnitude. Doing so, we normalize the value of the magnitude for each vertex by bringing the magnitude value within a range of between 0 and 1. And instead of overwriting what we already store in a key mag, we create a new key with the name norm mag, which stands for normalized magnitude. So when we run that line of the code, our point data dictionary is updated with new norm mag key that stores information about how fast the control point is moving on that particular frame. And I'm, for example, just print out the content of the point data dictionary for the vertex 53 at frame number 72, and it tells me that on that particular frame 72, the vertex with index 53 has this particular value stored. For the velocity, it's 0 because on the last frame there's no animation happening, that's predictable. And the normalized magnitude is also 0, the magnitude is 0, and the coordinates for that particular world coordinates for that particular control points is 0, 4, and 0 in Z. So from now, by now we collected all the information we need to be able to generate the texture map. So what we need to do now is to store these calculated values into the vertex of the polygon object. If we would be dealing with the particles, let's say if I go to dynamics and say particle tool, let's say just create a particle system here, right, like this. Let's just display those particles as spheres so we could see them. So we have 4 particles. I can right click and select each particle individually. And as you remember, we can add our own per particle attributes by just typing name of the attribute, my own per particle attribute name, right? For example, and I hit add, and you can see that we just created new attribute, my own per particle attribute name. And we could use this attribute to write any piece of information into the particle or any type of data we want. Unfortunately, in Maya, we cannot do that with vertices. Vertices instead only store type of the information that predefined by Maya developers. And by now, by the time of this recording, the only attributes that accessible in Maya to be stored is a vertex position in X, Y, and Z, which if you override them will move the point in 3D space, which not useful for us. The alpha attribute, which is a floating number, and then normal X, Y, and Z. And those attributes per vertex attributes could be displayed by going to Windows, General Editors, and Component Editor. So now there are third type of the attributes associated with the vertices, and those are the color attributes. So the color attributes are not displayed right now here is because they're all equal to 0. So what we want to do now is to use those color attributes. Let's say if I select this object, let's delete the particles. If I select the object and go to polygon module and say color, apply color, and I say apply, for example, a color of like something like this, right? Apply. So now each vertex was assigned a certain color information, and that color information is stored per vertex. So if I go now into Windows General Editors and Component Editor, you will be able to see that those attributes become visible: red, green, and blue. Red corresponds to red and green and blue. And what good about those is that we could use those RGB values to store up to 3 numbers. And then for this particular case, we would like to store the same number, and that number is normalized magnitude. If we store same number, normalized magnitude in all 3 channels, we will generate a grayscale representation of it, where 0 would be equal to black and 1 would be a full white. Later, we would be able to bake that per vertex color information into the texture. For this particular example, to illustrate this concept or that idea, I would like to open the file that I already pre-made. And that's the same cylinder practically. All I did, I selected object, right, in object mode, went to polygon module, color, and said apply color, and I selected red. And I assign to entire object. So if I go to Windows General Component Editor, it will show me that the vertices store information about the color in the red, 111. There is information about the green and blue, but they not display those columns missing in this component editor now. Is because those values are all 0. What I would do next, I would select, for example, the faces or vertices at the middle of the polygon, select green and apply, and then for the bottom portion I would select blue and hit apply. So now I have 3 colors stored per vertex. So now I would like to bake this per color shading of this object. Once again, if you take a look at the hypershade, it's not really a shader itself that is assigned to this object. What we see here, we see the per vertex colorization. There is a way to convert per vertex color information into the texture, and that would involve using a mental ray as a renderer. And the command that used to bake the texture could be found under rendering module, and it's under lightning menu and called batch bake mental ray, and it displays us quite detailed, full of options dialog box here. We can reset it to default like this, and as you can see, it takes a use of so-called texture bake sets. There's a quite advanced topic on bake sets in Maya and how to deal with them. In short, I would just describe that you create a bake set. It's some kind of procedural node in Maya, and you specify certain attributes within it, such as what kind of information you would like to bake, whether it's a light and color, lights only, global illumination and such. Then you specify resolution of the texture, the file format, the depth, and how many samples you would like to take during calculation. The thing is that in order to bake the color per vertex color into the texture, there's one more step you need to do before you run a lightning batch bake command, and that would be creating a surface shader assigning it to the object, right? And then you would need to create a node which is called mental ray vertex color. So if I select surface shader that I just created and I say click out color swatch, and then I can type here vertex, make sure that mental ray is visible, and you can see by typing kind of keyword for that shader or for that shading node, you would be able to filter. And you see it's mental ray vertex per color right here. And then you need to create a connection between, actually you need to create a connection between the mesh shape node and mental ray vertex shading node that you just created. And that connection is actually the output attribute is a color set and a color name. You can see it on my screen. And the input connection and mental ray vertex color CPV sets 0. Then you assign this shader to the object if you didn't assign it yet. Now with this shader assigned and the connections made in this particular fashion, you can go ahead, select the object, go to Lightning, and say batch bake, and start generating the texture. You would need to create a bake set itself, and it's called initial texture bake set. And it comes with the attribute editor, which is very similar to the one that you see as an attribute editor for the command itself. We don't want to use bake set override during calculation of the texture generation. We would like to use initial texture bake set instead and modify it. So that's a kind of outline of the steps that are needed to convert per vertex color information into the texture. As you could see, the Maya built-in convert mental ray baking option tool does not allow us to bake it on a frame-by-frame basis. So our tool needs to be flexible enough or powerful enough to do it on a frame-by-frame basis. So we would need to write our tool to be able to do it on a frame in advance, frame by frame. So for doing so, we return back to our script, and after we arrive to the point where we store and calculated all the information about the object control points into the point data dictionary variable, we now ready to proceed to first of all create the vertex and texture bake sets, the one that are required for the texture baking and process to work in Maya. And we would do it procedurally by running it from a Python script. The command to create a texture bake set and vertex bake set is the same. It's a create bake set mel command. And then we just specify the flags and attributes. The ones that I've got here, I got from documentation, and they're very similar. All you do is just change in first line. If you want to create a vertex bake set, you create a vertex bake set. You specify a vertex bake set. If you want to create texture bake set, you use the same create bake set command, but with the flag texture bake set. This time we don't convert a mel command into Python by using CMDS, like we did in all other examples. This time we utilize a powerful mel-eval command, which is actually a very simple way to convert any mel syntax code into Python executable. And that's what we see here I'm doing. I use mel-eval, and then exact syntax of the way it would be used if I would run a mel script. Whatever happening inside of this bracket using mel script syntax is being evaluated by Python by using a mel-eval command. The output of this line is a Python output, and we feed it into the vertex bakeset variable. We call it vertex bakeset. And it will store the name of the vertex bakeset we just about to create. The same we do with the texture bakeset. We run, evaluate, execute this command through using a mel-eval Python command, and the output of this command goes straight into Python variable texture bakeset that in this time will receive the name of the texture bakeset node that we will be using later. Since we just created texture bakeset, we're now able to modify its attribute through the command line. And all we do is, instead of like if I would do and change those attributes using a click operation, we could do the same modification by using set attribute command. And I'm sure you're very familiar with this set attribute command. It's a mel command. This time we switch back to CMDS instead of mel-eval. But if you would like to, you can keep using mel-eval if you feel comfortable with. The first, we use a texture bakeset variable that stores the name of the bakeset that just created. And then we use a very simple plus operator that we plus two strings together. The first string is the name of the texture bakeset, and then the name of the attribute. We, as an argument, as a flag, or we equal it to the value that we would like to define. So we set resolution, samples, bits per channel, file format. So by the time we finish this line, we not just created texture and vertex bakeset, but we also set up certain attributes for it. In order to keep the script simple enough, instead of like keeping those lines one by one here, like after we finished with our point data dictionary, I could just do this kind of things here. So I just could continue creating a bakeset line after line. But in order to just simplify the code itself, I would define a function that I call a Python function, which I will give name create bakeset. And I'm using a Python syntax for function definition, which is a def. That's something that you would do a lot of times, declaring the functions, so the syntax for that becomes a second nature really fast. After you run your executable lines, often you would like to return some pieces of information from a function, and you do that by using a return command. Return command can return one variable if you want, like this, or you might return multiple variables by putting them in a bracket and separating by comma. So next, after the texture bakesets are created, we create a shader similar that we created in a Hypershade, not a similar but exactly the same, really, like this. We create a surface shader. we create a mental array vertex color node. We assign mental array vertex node we just created and plug it into out color swatch. And then we create a color set for object, and the color set per object only can be created by assigning color information to the per vertex. As soon as you assign, if for example I create a polygon sphere, for example, right, default one, and I move it to the side, there is no per vertex color information associated with this object. So if I would attempt to link the shape node of this sphere to mental array vertex color node, this relationship could not happen because there is no color set assigned with or associated with this sphere. And please don't confuse color set with the texture or vertex bake set. The color set is a special node in Maya that is being linked to the object shape node, and it's responsible to store the per vertex color information. So for example, if this object that I just created from using the create polygon sphere menu, if I select all vertices or just one vertex or faces or so far, right? It does not really matter what I'm selecting. Let's say I created just a few vertices, selected few vertices, and I would go to polygon module and select color, apply color, and I say apply, then assign from those vertices being assigned the color, now this object, this sphere, is now also would have those needed color set associated. So now, even while only several or few vertices were colorized, the object, the shape node of the sphere is being linked to the attribute was created that is needed to connect the shape node of this object to mental array vertex shader node. So this relationship between the sphere and the shader can be established, and so having this relationship, we would be able to generate a texture or bake color information of the object into 2D texture. I know it sounds confusing, but please study the file that I'm saving with this lecture, and it will illustrate this shading network in quite simple, understandable way. There are only like really 3 or even 2 nodes involved here. It would take longer to describe them verbally than just by opening their attribute editor and study the arrows in a hypershade. By placing your mouse over the arrow, you would be able to see what exactly attribute to what attribute is connected to, so you know for sure what's going on. So when this shader is created and the relationship between the shape node of the object is linked to the mental array shader, now you're able to proceed to the rendering menu, rendering module, lightning, and batch bake mental array. Strange, they call this tool batch bake, because batch bake, as I understand, supposed to happen with multiple times, or like a batch in a row. But batch bake only works one single frame at the time. So that's something we would need to address in our script, since we're interested in generating the texture frame by frame basis, because our texture needs to be animated. So return back to the script editor and get to the code. So by now we finished a vertex bake set and texture bake set creation by calling a function that calls createBakeSet. And just to refresh the memory, is that createBakeSet function creates a vertex-bakeset and texture-bakeset. After the texture-bakeset is created, we modify its attribute by using setAttribute command. After we finish modifying the setAttribute or using setAttribute command, we return back to the bottom of the script from where we call createBakeSet function, returning back the name of the vertex-bakeset and texture-bakeset nodes by using the return command and specifying the variables that we're returning. Those values that are being returned inside of those variables, vertex-bakeset and texture-bakeset, we capture into our own variables. And please note that I'm using different names, the very similar names for the variables, but with different names. This doesn't have an underscore, and the name starts with the capital letters, while the variables that capture results in variables use an underscore in all lowercase. I made it purposely to illustrate another benefit of functions is that the variables inside of the functions are local to the functions, meaning if you declare a function, a variable inside of the functions, those variables stay locally, not accessible from outside of this function. So next we would be creating a shader, and for this purpose we also will declare or define a function. We call that function createBakeShader. We specify that function underneath the createBakeSet function. So it's the next function to use, makes sense. We specify that this function will receive two variables. One variable would be called object name, and other is object shape. So every time we call this function createBakeShader, we will send to this function two arguments, so-called object name in our case and object shape. Those names are needed by Maya for certain commands that we will be using inside of this function. So let's just go line by line inside of this function createBakeShader and see what exactly is going on. First of all, we will be using meleval command that would allow us use a mel syntax to run inside of Python. We use a set command that will create nothing but just an empty shading group. A shading group is the one that you're familiar with. Is every time you create a shader inside of Maya, let's say Blinn, right? You would be able to see that even while you created the Blinn shader, it's already connected to shading group node. So they kind of go parallel to each other. And where Blinn is actually kind of a child of the shading group node. So shading group node is kind of makes everything possible, really. It's even got its own attribute editor. So for this particular reason, before we create a surface shader, which is this is a surface shader, this is a shading group node. So before we create surface shader, we start with creating the shading group node. Okay, so the shading group node here is created on the first line, and we capture the output of this command, create shading group node, with the name BakeSG. That's it is right here, and we store the name of this, which we already know what the name is because we give it a name, to the variable sg. Next we continue to the next line, and this time we create a shader, surface shader, and we capture the output of this Python command. We're not using meleval for this particular example, into the variable surface shader. Before we create any other node, we create connect attribute. We use a connect attribute command to connect attribute of the surface shader to shading group node, and that connection can be seen right here. Bake surface shader out color to surface shader. And you can see we use exactly the same syntax here. The name of the attributes is right here. So we say CMDS connect attribute, surface shader name, there is just stored in a variable, out color, and then next attribute that we're connecting to is a shading group node name, which we store in as G variable, and we specify force true. So if by any reason Maya complains and refuses to connect those attributes, do your best to connect them. Next thing we will do is to create this node, mental ray vertex, and very similar to the one that we used to create a surface shader. Instead of this time we use mental ray vertex color as an argument to create node command. Right? So if, for example, I run this command just to illustrate the idea, you can see the created node pops up here. If I do this with the surface shader line, it will create a surface shader here. If I create a shading group node, it will be created there too, but we're not able to see it because it ends up filtered from work area, right? So I hope you understand where I'm going to. So we step by step recreating shading group, surface shader, mental ray vertex. As we create them, there is no connection between them. So every time we create something, we need to connect them. We create something, we connect them. So for that particular reason, our line of code is mixing with connect attribute, create node, connect attribute. So they kind of self-repeat themselves, just with different shading nodes or attribute names. Okay, so let's move on further. After we created this shading network, we're ready to assign it to the object. So what we do, we select an object that we know the name, and name of the object we know because we send it to this function as an argument, and then we select with toggle to true, meaning like we shift select, like a multi-select, instead of reselecting things like you would do with your left mouse click. You would toggle, meaning you would add to selection using a shift left mouse click. So you add to the selection. That's what we do here. We select object first, and then we add to that selection surface shader. And then, while both object and the surface shader are currently selected in Maya, we execute command cmds set and add it to true force element equal to SG, where SG is a shading group, the highest node of the shader that we created. So this particular command will finalize the creation of the shader and assign it to the object. We exit this function create bake shader with name of the surface shader that we created and assigned to the object. When we return back to where we left by the time we call the bake shader option, we're ready to bake. And we would bake by calling bake function, which is the last function of the script. And what that function would do, it would go for each frame in a range, first frame, last frame. That's something that we already discussed multiple times within this script. And then it would say, first thing it would do, go and advance to the current frame. So for example, if we first frame is equal to 1 and last frame is equal to 100, the first frame in the range will be first frame 1. So the current time or the frame would be 1. So this command here would move the time slider to frame number 1. As soon as the time of the Maya frame range, not frame range, but current time changes to that frame, we're ready to execute the command. And the command would be going in a loop. First we do is a color assignment. So for each vertex index stored in a point data dictionary, and you remember that point data dictionary, first key in that dictionary is the vertex index. So for each vertex index in that dictionary, do following. Read normalized magnitude stored in this particular frame for this particular vertex index. Here's the full path to where that normalized magnitude value is stored. Then select none, nothing, just to make sure that nothing is selected in the sphere. I mean in the scene. Then select vertex itself. Because in order to assign a color to the vertex, we need to select it, just like we do here in a viewport. If I select object, right click, and I say vertex, and I click that vertex, what we did, we selected this, we run this command, select our mesh vertex and index of the vertex. If I select another one, you can see the index of the vertices changes. That's what we do here on vertex by vertex basis, stored in the point data dictionary. We select vertex by vertex, but before we deselect anything, before we advance to the next vertex in a row, we assign the color, normalized color, that we store in normmag key as a per vertex color attribute that we observe using general editors in component editor here. And you can see red is here, right? And green, blue, if we would be storing it there. So by going through this loop here, all we do, we read normalized magnitude value stored for this particular vertex that we're processing right now, at this particular frame that we are currently time frame is on. We read this data from a point data dictionary. We deselect everything before doing anything. Then we select the vertex itself that is currently on, and we assign that norm magnitude that we normalize between 0 and 1 as the color per vertex. And since we assign it to red, to green, and to the blue, then this color will appear to be as a grayscale, meaning it will not have a colorization. All RGB values will be the same. When the color is assigned to the vertex, and before we move on to the next frame, we bake that texture. So we process from a vertex with index 0 to the last vertex index. All of these vertices on this particular frame were assigned corresponding norm mag value as the color. So now all the vertices represent by their color their own speed. Now all we want is to bake this per vertex color into the texture. And since we already created a shader, mental ray shader, in the previous step by calling create bake shader function, we know that the object is bakeable, meaning like it's ready to be used to convert per vertex color into the texture. So that's what we do here. Is a bake result is a variable that we assigned to the output of never by now used command, and that command is convert light map setup. Light map setup is a mel command. We use CMDS as always did, almost always 95% of the time, and we give it certain flags and attributes. Full documentation is available in MayaDoc, but those are required. We specify the camera, which hard to understand. Why would it be perspective? CH is true. Keep original shading graph true or group true. Show CPV and bake set override to initial texture bake set. From my testing and playing around with this particular tool, I came to conclusion that the bake set that we created using the first function, create bake set, and as you remember, it was a line of the code that we started calling our custom functions. Here was the first one, needs to be importantly called initial. We need to give it initial texture bake set by some reason. So that's what we do here. We specify, when we bake the texture, we specify the name of the texture bake set that we created by calling create bake set function here. So when we created texture bake set node, we specified its name right here. So the second word inside of the bracket here, the first word is the name of the mel command. The third word is the type of the node that or the set that we want to create. The second word, or the word in the middle, is the real name as it appears to be in Outliner. By some reason, it needs to have exactly the same name as I use in here, and by now I could not find any way to customize this name. And if I use any other name for the texture bake set, the command fails to execute successfully. I've got no issues of having this texture bake set name as an initial texture bake set, but I wouldn't mind to know why I would have to use initial texture bake set for this particular tool to work. So anyway, CMDS convert light map setup receives certain arguments and flags specified inside of this bracket. The first is camera. We specify to perspective. I'm sure it can be any other camera. It does not make a huge difference on this particular command to work. The last attribute or flag, we specify what bake set override to use, and we specify as an input the name of that texture bake set we created earlier. We capture the output of this into the variable bake result, and interesting that the bake result will be receiving a name and a full path to the texture map or image that will be generated. So the bake result variable will store the full file path to the texture along with its name. So for example, if I'm working in this particular scene, right, in this particular project, and I know that all mental ray generated textures go to name of the project, render data, mental ray, light map. This would be the folder that it would be going to by default, and there's no way to override it. Okay, Python would need to append every / character to double to work properly. Another way, you could do forward slashes and you could go away with a single one, whatever you prefer to use. So for example, I know for sure that that it goes in this particular folder. So the bake set result variable, after running map generation, will be given a full path to the file, and then the name of texture, and depending on the type of the texture, it will be extension dependent at the end. So I most of the time find that it's not exactly what I want, and I would like to rename this texture to something else. For this particular reason, I reassign back result variable, which is a list, to a new variable which I call source. And since it's the bake result variable receives a list with only one index at 0, which stores the file path to just generated texture map, I convert whatever is stored in that particular list index 0 into the source string variable, and I'm using a string Python conversion to make sure that whatever I stored in a string source variable is a string. So result of this, it would be a clean, nice variable, string variable with the file path to the just created texture map, like this. Right? So now so if, for example, I create this variable bake result just to illustrate the idea. Next thing, I'm using OS path basename Python function to tokenize or extract the name of the file from entire file path. That's what the power of Python kicking in, especially because it's got certain command set that allows you to take a string that represents the file path and extract all pieces of information you want, such as file path to the file from entire file path, the name of the file itself, the extension of the file, and so far. So for the base name, I'm using a basename, OS path basename Python command, and as you can see, I know what the name of the file is. The next line, I'm using a split extension, and as a result, I know the file name itself without the extension, right? File extension. So I'm knowing the name of the file without anything that precedes. And for the file extension, I'm using the same command, except I'm reading the last index of the list, which would be file extension itself. And then I use OS path dir name to get idea what the file path is to the file. So now this line here, those 3 lines, 4 lines, were used to so-called tokenize or extract the data from a file path. I'm here on this line. I end up knowing our file path, the file name, the file extension, and the file base name, which is a file name plus extension. So now I create a string variable that I call frame number. And frame number, I give a single frame a number which is in the integer, right? And it's probably, for example, right now on frame 11, it would be frame 11. And I'm using this particular syntax, which you could find in Nuke, for example, used heavily. But it's really a Python-based syntax. It's not a Nuke-based, for example. And what it allows me to do is to keep the numbering consistent. Result of the frame number is as many numbers as I specify with this particular syntax, and it's a string instead of the integer or float. So let's take a look. Oops, sorry, by some reason I mean type. And it shows us it's a string. Okay, so now like having all these ingredients together, I'm able to combine a new file path, okay? A new file path that I'm building out of using this ingredient is my destination file. And you can see that the file name I started with was something very different from what I arrived to, right? So it used to be like a bake SG low res, something like this, and now I'm giving it a file frame extension, frame pattern that sits between the file extension and file name, and that would be repeated for each frame. And the very last command for this particular example is OS rename, and that would accept source file path and destination file path, which is actually from what you want to rename to what you would like to rename. And that would be the last line of this code. I'm sure there will be slight modifications made to this code by the time we write this dialog box, because right now all the resolution values, samples, texture type, and the bit depth, as well as the directory to where the image is being written, is baked into the Python script itself. We would like to make sure that those values are overwritten from the dialog box, or values used in a dialog box. And that's why we would like to return back to this original script and make a slight modification to it. And that's the main reason behind of using the functions here, such as a create bake set, create a bake shader, and a bake. The reason why I switched, or not switched, but started to utilize the functions is to make sure that when we get to the graphics interface writing, we deal with some piece of code that is easy to revise. So for example, if you return back to this code later, I'm sure it would be really easy to find the place in the code where you create your texture, where you bake your texture, where you create your shader, where you create your bake sets, where you modify your bake sets. And as you can see, the name of the functions themselves we use, they're self-explanatory, such as like a create bake set. Then even if you return to this code like 6 months after, you would be able to say, oh yes, I know this portion of the code deals with the bake sets, and this particular portion of the code would deal with the bake shader, and this particular portion of the code would deal with the bake texture. And since I didn't put this here, but I commented it heavily, then it probably would be something step by step, and if I read carefully, I would never get lost and such. And some Python programmers like to break down the functions to only 2 lines of the executables, meaning like you would use one function to create a vertex bake set, and another function to create a texture bake set, and then third function to modify the attribute of the texture bake set, and fourth function to modify the attributes of the vertex bake set, and so far and so far. So they would end up with like 50 very small functions that they will call. Another reason why you would want to use the functions is, aside from having your code simple to use, is that you also would be able to reuse the same lines of the code again and again and again and again. Because let's say if there are some places in your code where you would be calling the same function or multiple times, it's instead of retyping the entire command again and again and duplicating the code in your script multiple times, it's better to spend just a little of time specifying, defining a custom function and calling the function instead of using the entire syntax again and again. And aside from that, the functions is the entry level of the classes that you would like to use later when your knowledge of Python advances a bit. And with the classes, you open a door to object-oriented programming, where things become even more interesting and exciting. So it's just the beginning of the kind of scratch. If you're able to grasp the idea about the functions, about the passing the arguments, receiving the arguments, local functions, global functions, variables and such, returning variables, returning values from functions, and step into the world of object-oriented programming. That's a destination where you pointing to while learning Python and any other programming language. So I highly recommend you not to disregard any pieces of information that I outline here, and I did my best to keep the code as simple as possible, and without like a repetitive code or using the code that wouldn't be not much beneficial, make no difference in running. So please study, ask yourself questions. If you don't know how to answer, ask me on a forum, and create as many tabs as you want in your thing. Copy paste portion of the code you don't want, break down line by line, advance, because any programming is a trial and error process, meaning like you fight with the line until you break it down and fully understand what each a line of the code does and what it would do in multiple scenarios. The more you know about the command, the more you anticipate and able to predict the output of the command, the more knowledgeable you with the script, with the Python or other programming language are. Unfortunately, you can see this class already taken a while, and I'm absolutely on not enough time to get deeper into the conversation about the programming and writing and custom tools and such. But I hope that you given a clearer conceptual sight of what programming is and how you manipulate the data and pass information back and forth, and how you put this strategy together right in your code. Okay, I see you next week and we will move to graphic interface and such. Thank you very much. Bye.